Good evening, Year 11, and welcome to your night before last minute revision before your physics exam on Monday morning. What we'll be taking a look at this evening are one of the required practicals that you did at the end of Year 10 rather than having done it in Year 11. So the one that you'll be least familiar with in terms of when you did it last. We'll also then take a look at some of the key points from the beginning of the Year 11 topics, and then just to round off a couple of sections on some common errors and how to avoid them. So, in terms of required practicals, this is the one that we carried out during Year 10, but it does come up again as part of the forces topic in Year 11. And this is the extension of a spring required practical. It's also known as the Hooke's law practical. For this practical, the independent variable that you are going to be changing is the weight that is added to the spring. The dependent variable is the extension of the spring. So you would be expected to measure the length of the spring before you start, so that you can then measure how much the spring has stretched by when you add weight to it. Alternatively, if you position the ruler so that the zero of the ruler is level with the bottom of the spring before you start the experiment, then as you add weight to the spring, you can measure the extension directly. So, doing that over a range of weights and measuring the extension, you will be able to apply the equation for Hooke's law. So the Hooke's law equation states that force is equal to the spring constant of the spring multiplied by the extension. This means that the extension is directly proportional to the force because the spring constant is obviously a constant. So as you double the size of the force, you would expect the extension of the spring to double and so on. Notice the units we use here. Forces, as always, measured in newtons. Extension needs to be measured in meters. The units of the spring constant are newtons per meter. If you are given this in a calculation question, they sometimes do give you extension in centimeters. You would be expected to convert them. When you plot a graph of this, you will find that you get a straight line. That straight line should go through the origin. That tells you that the force and the extension are directly proportional. But the gradient of the line also tells you something about the spring. So a stiff spring, which is one that has a high spring constant, requires a much larger force for a smaller amount of extension. And so the graph, as you can see here on the left, will be quite steep. For what we describe as a soft spring, that is one that has a very low spring constant. Very little force is required to produce a very big extension. So as you can see here, the gradient of the graph is much shallower. You could be asked to calculate the spring constant, and to do that, you just need to calculate the gradient of the graph. So, as always, when you're calculating the gradient of a straight line, if you construct a triangle underneath your line of best fit, and then calculate the change in y value between those 2 points on the line, and the changes in the x value between those 2 points on the line, the change in y divided by the change in x will give you the spring constant that is equal to the gradient of the line. One more thing that you can get from the graph showing the spring constant and extension, etc., is the amount of energy that is stored in the spring. The amount of energy is equal to the area underneath the graph, which, as you can see here, is a triangle. The area of a triangle, as you will know from maths, is a half base times height. So if you substitute in for the fact that the base is the extension and the height is the force applied, That gives you this equation that the energy stored is equal to a half Fe. However, from our Hooke's law equation, we know that F is equal to Ke, the spring constant, times the extension. So that gives us that the energy stored is a half times K times E, otherwise known as a half Ke squared. And that is the equation for energy stored in a spring that we first introduced you to back in year 10. The other thing that comes up in relation to this experiment is when springs or other stretchy objects stop behaving in an elastic way and no longer return to their original shape. And that can be clearly seen from a graph because the line will no longer be straight. So when a material has been taken beyond its elastic limit, the line begins to curve. And then when you take all the weight off of it, it no longer goes back to its original shape. All the time it is obeying Hooke's law and behaving in an elastic way, it will always return to its original shape when you remove the weight. Okay, moving on to some more recent content. Waves was the very first physics topic we looked at this year. You do need to know that waves are caused by vibrations, otherwise known as oscillations, and that waves transfer energy. That is something that all waves do. But the waves do come in the two types, as you can see on the screen here. So a longitudinal wave is one where the direction of the vibration is parallel to the direction of the energy transfer. The main type of longitudinal wave you need to know about is a sound wave. This is how sound travels through the air, through water, and through solids. If you are doing triple science, the other type of longitudinal wave you need to know about is the P-type seismic or earthquake wave. The transverse wave is where the direction of vibration is perpendicular to the direction of energy transfer. This is the vast majority of waves. It includes waves on water and all of the electromagnetic waves, the different types of light. Additionally, if you are doing triple science, it also includes the S-type secondary seismic wave. This is the type of wave that makes the buildings shake from side to side. In terms of the properties of the waves that you could be asked to identify, when you have a longitudinal wave, as you can see from the diagram here, you see areas where the material the wave is traveling through are bunched together and areas where they are pulled apart. The regions where they are bunched together are called compressions. The regions where they are pulled apart are called rarefactions. Please be careful of the spelling of that word because it's very similar to the word refraction, which you may come across if you're doing triple science. The other characteristic of a longitudinal wave you need to know is the wavelength. The wavelength is the distance from one compression to the next compression or one rarefaction to the next rarefaction. For transverse waves, they're a little bit easier to label, and there are three main properties that you need to be aware of. The first one is the wavelength, which is the distance or the length of one complete wave. The easiest way to measure it is to pick a point on one wave and go to exactly the same point on the next wave. And the easiest places to do that, as you can see on the diagram here, are when you go from the peak of a wave to the peak of the next wave. That also means that your line that you draw to identify the wavelength is off of the actual picture of the wave, so it doesn't get in the way. When you do label your diagram like this, please make sure that the length of the arrow you choose covers the whole distance from one peak to the next. If you draw your arrow too short, it'll be marked wrong because it's not marking the places correctly. The second characteristic is the amplitude. The amplitude is the maximum distance away from the rest position or equilibrium position to the top of a peak or to the bottom of a trough, as you can see from the diagram here. So for each wave, you can mark the amplitude in two different places. So it's half the total height of a wave from the midline to the top or the midline to the bottom. The amplitude of a wave corresponds with how much energy it's carrying. So for a light wave, a big amplitude would indicate a brighter light. The third property is the frequency, and that is the number of waves per second. That is measured in units called hertz. So if you look at the pictures here, you can see there are two waves. The second wave, there are more of them in the same amount of time, and therefore that one would have a higher frequency. And the final property of a wave that you might be asked about is the time period of a wave. That is the time taken for one wave. And you can find that using the equation time period equals 1 divided by the frequency. They are inversely related to each other. That equation is on the equation sheet that you're going to be given. So as the frequency of a wave gets bigger, the time period for a wave gets smaller, and vice versa. Finally, just to round off on a few things that often crop up as common errors on exams. And the first one, as you can see from the example here, is when you're doing calculation questions and you've been given some of the numbers but not in the correct units. So in this case here, for example, we've got the momentum and we've got the mass, but the mass has been given in grams instead of kilograms. So we'll start with the equation. When you substitute the numbers in as given in the question, you will then get an answer which is close but is not the right answer. If however you show all the steps in your working, you can still pick up some of the marks for this type of question. However, to do it correctly, you need to make sure you convert into the correct units. So to convert from grams into kilograms, you divide by 1,000, and then you can substitute in the corrected value, which will then give you the right answer. Don't forget, if you've been asked to give the unit as part of the question, there's always an extra mark for giving the unit as well, so please make sure you include it. The second common error occurs when we are dealing with mass and weight. Mass is measured in kilograms. It's a measure of the amount of stuff that you are made from. And it doesn't matter where you are. You could be an astronaut on Earth, you could be an astronaut on the moon, or in any other planet. Your mass is going to be exactly the same wherever you are. However, your weight is the force of gravity acting on your mass. Weight is measured in newtons. And because gravity varies from location to location, then your weight will also vary. So on Earth, where the gravity is higher than it is on the moon, you will weigh more. On the moon, you will weigh less, even though your mass is exactly the same. If you have questions about other planets, if the gravity is higher on other planets, your weight will be higher. If the gravity is lower, your weight will be lower. Please don't get those two things confused. And finally, just to finish off, coming back to the forces topic again, take a look at the graphs on the screen here. The top row represent distance time graphs. The bottom row represent velocity time graphs. And they look exactly the same. However, they do mean completely different things. The diagonal upwards line on a distance time graph represents an object moving at constant speed. However, the same diagonal line on a velocity time graph represents constant acceleration. Similarly, the horizontal line for the distance time graph represents an object that is not moving or is stationary. However, on a velocity time graph, a horizontal line like that means constant speed. So if you do get questions about distance time graphs and velocity time graphs, please check very carefully the axis label on the y-axis and to make sure that you know which type of graph you are dealing with. Okay, that will do for tonight, Year 11. Enjoy the rest of your weekend. Enjoy your physics exam on Monday. We will see you again soon.